Today, I'd like to welcome everyone to the second day of the 2024 series of Noble Lectures, and welcoming our speaker, Professor Elliot Tziperman from Harvard. So today's topic is one of his central works when he takes the position of sorry. Yeah, okay. This is one of his central works when he takes position as the professor of oceanography and applied science at Harvard, and by evaluating model performance with climate reconstructions from proxies during times when greenhouse gas levels are comparable with what we have today, we are able to gain some insight on how climate models perform, which help us evaluate and improve our models, and also on the climate science change, which is unfortunately going to have an imminent impact on us, and which Professor Tziperman teaches at Harvard University. And given the topic of today, the materials we hear today might be exceeding what's contained in Professor Tziperman's newly published book on global climate change science. So let's welcome him.
Thank you.
Careful not to go to the left because that connection is.
Great. And hopefully everyone can hear me in the back. Morgan, don't you want to move forward, Morgan? Would love to have you here. Sounds good. Okay. This is a subject that I love getting back to. So the original papers are like 10 years old, maybe even more, but more recent students of mine have gone back to this problem again and again. So it's something I am really enjoying. So two different subjects, the wintertime Arctic convection and low clouds over North America, together trying to explain what might happen or what might have happened in the past for very warm climates. And this is the work of Dorian Abbott, who was a student, Tim Cronin was a postdoc with me, and several others, as you'll see. Okay, so let's start by introducing this. So this is what an Arctic air event looks like. You have very cold air forming over Canada and then being advected toward the US. This is a particular event in Samir. I don't have the year here, but you get the idea. Very cold air forms here and propagates southward. So this is what happens every winter today. This is what this area looked like 50 million years ago. So tropical, nice, above freezing winter temperatures. That's the critical part. So the winter temperatures were above freezing. That's pretty amazing. As you'll see, there's evidence for that. And let's see if I can actually make this work. That would be kind of nice. Maybe not, fine. So what we're trying to explain is these above freezing winter temperatures. And so the first part will be the idea that if you have low clouds over the continent, due to moist air arriving from the ocean in a warm climate, these low clouds can keep the continent warm and above freezing. That, again, that is the huge challenge here. And the second part is air that comes to North America in the winter sometimes makes it all the way from Siberia over the Arctic into North America, including both Canada and the US present day. And for that to work, if the Arctic is ice covered, that won't work. So you need to remove ice from the Arctic. And one way to do this is the second cloud feedback that we're proposing. So that would be wintertime convection. So the same convection that happens at the present in the tropics, we're proposing happen during winter with no sunlight over the Arctic. So it's a pretty radical suggestion. And I'll get back to that. So these are the two cloud feedbacks that I'm going to discuss. One is low clouds, basically fog over North America. And the second one is these convective clouds over the winter Arctic that help eliminate sea ice. That's the plan for today. Okay, and these are some of these papers. Okay, so starting with this is an event from 2014. You get the idea. The temperatures are -40 to -60 with wind chill, and it's unpleasant and takes your skin 5 minutes to freeze if you're outside. I mean, you guys lived through this. It's hard for me, admittedly. Okay, here's the period we're talking about. So we talked about the Pliocene yesterday, 2 to 5 million years ago. Now we're talking about this period. This period is a bit different, much warmer. So what's shown here is deep ocean temperature, and you can see that the deep ocean was like 12 degrees maybe. There's a huge amount of uncertainty here, obviously, but say 12 degrees, that means that the poles were 12 degrees because this deep ocean temperature is water sinking at the poles. So if the temperature of the deep ocean is 12 degrees, that must have been the temperature in the Arctic as well. And what do we know about it? We know that we find fossils of alligators and palm trees. And these things, and other small plants, and these things cannot sustain sub-freezing temperatures. So that means that for maybe millions of years, or at least thousands of years at a time, there wasn't even a single night of sub-freezing temperatures over places like Wyoming, present-day Wyoming, which is pretty shocking given what's happening today, right? And we're trying to explain how that's possible. Any questions about this so far? Okay, and here's what we know about this Eocene period. And again, this is relevant, as you'll see, also to future climate, but let's start with the Eocene. So the continental configuration was not super far from today's, which is why this is a relevant period. If you just go a few tens of millions back in time, then this thing would look completely different, the supercontinents and all that. But this doesn't look too different. You know, the jet lag flying from the Middle East to North America would have been smaller for me, so it might have been a better time for me to live then. But other than that, things look similar. Australia is further to the south. India just collided with Asia and so on. And what do we know about that period? So high global mean surface temperatures, a low equator to pole temperature gradient, maybe 25 degrees, the equator to pole temperature difference, while today it's about twice as much, above freezing winter temperatures, which I emphasized. Weak seasonality, no ice in Antarctica or Greenland. CO2, we don't know. And this is often referred to as equable climate, which means that the equator and poles are equal to one another in a sense, and also the winter and summer are equal. So that's referred to as equable climate or warm climate, and so on. Again, questions? Great. Why do we care? Well, because, you know, future projections under business as usual tell us that the temperature, the global mean surface temperature might increase to a level that's not far from the Eocene. And if you look at sea ice today, Arctic sea ice, this is what it looked like in 78. This is what it looked like in the year of minimum sea ice so far, 2012. It's not very far from that today. So it went down dramatically, like 50% of the Arctic is not ice covered in September. But last year, it's even worse in Antarctica. You probably all saw this. This is the ice cover over Antarctica, and this is 2023. Look at this. These are all the other reasons. This is 2023. Isn't that amazing? I mean, shocking. Until last year, we kept telling people that Antarctic sea ice hasn't responded yet, but now this is like 5 standard deviations from the normal or something. I don't know how many. Pretty shocking. Okay, so we're making good progress toward past-warm climates. Okay, so the first part is this Arctic air suppression. So let's talk about how Arctic air forms in the present-day climate. So for that purpose, we're following Judith Carey's 1983 formulation. So you take a column model of the atmosphere, just a single column model, and you pretend that it represents an air column moving from the Pacific Ocean with the westerlies to North America. So you start over the ocean. This is day 0, and then you move it over North America. By that, we mean you simply change the boundary condition at the bottom to be something that corresponds to snow or thin ice cover and so on. And then you let the temperature evolve. There's no shortwave radiation because we're pretending very close to the Arctic Circle in wintertime. So within 2 days, you get a cooling of about 15 degrees Celsius. And within a few more days, you get the cooling at the surface of -40. So going all the way to -40. So that's how this Arctic air forms. Just you move it over land. It doesn't have the warm temperature of the ocean, relatively warm temperature of the ocean. It cools, radiatively cools very rapidly. And that's what you get. So, and then this air gets advected south and might have killed the dinosaurs and crocodiles and palm trees and whichever you wanted that period. Questions about this part? Okay, so again, this is just reproducing what Judith Carey did. So now let's see what happens if we start the air column with much warmer temperatures. So now day 0 is 20 degrees instead of being 0. So the vertical axis is pressure, The different lines correspond to different days after the initial conditions. And in this case, after 2 days, again, the initial temperature is pretty large, like 10 degrees. But then after that, you get the lines to sort of be crowded here, which means that there's no much cooling happening for the rest of the, say, first week. And that means that the surface cooling is suppressed. So what happened here is the question. What happened that prevented the surface cooling from continuing as it did in this case? So instead of getting minus 40, you get only a cooling of about 10 degrees, maybe 15, and you're still above freezing for a long time. And by the time this gets below freezing, this air moves off North America and is replaced by another air. And we're trying to understand why is it, what prevented the air from cooling. And the green bands here are a hint, because green bands means water clouds and blue here means ice clouds. So clouds develop in the lower part of the atmosphere, as we'll see in a second, preventing further cooling through a long wave radiative effect. And I want to stop here and see if there are any questions so far, because now I said something about our own work. I'm going to show that in 1 second in the next slide. So I'll show how the long wave cloud effects prevented further cooling here. Okay, looks like we're good. Great. So here's what happens. So we look at the orange lines, which represent this warm climate simulation. You have in the background, the purple ones show you the cold climate simulation, but we're interested in the orange lines in all of these panels. So here's what happens. First of all, you can see that the temperature initially cools. You can see this initial cooling, but then plateaus for a long time. Okay, that plateau is above freezing. The freezing line is here. So you can see that the plateau is above freezing. And this also shows you that the net long wave cooling at the top of the atmosphere was large initially during this very brief, strong cooling of about 10 degrees. But then the net long wave cooling at the top of the atmosphere weakens dramatically, basically to zero. And the reason this happens is that you have these strong liquid clouds developing. So cloud fraction is large. And as a result of that, the greenhouse effect of these low clouds prevents long wave from escaping from the surface, and that leads to a plateau in the temperature. So that's why the temperatures don't cool from day 2 to day 4 to day 6 to day 8, maybe even. And this way, for a long time, the air remains above freezing, and these alligators and palm trees can survive. Make sense?
So you comment on the inversions that are forming in that period above, the sphere, but above the surface.
Right. So there was a strong inversion, as you saw before. A strong inversion developed in this case, but not much in this case.
The atmosphere above.
This. Yeah, yeah, it's basically that. I mean, you have cooling at the top of the cloud layer. Yeah, exactly. Nice. Yes. This thing does not have anything but a single column physics, so it doesn't have that. I'll get into. You have some additional information about what the convection is? No, at this point, nothing like that. It's just very heuristic. I'm saying, in principle, the air would move off the continent, but I'll show you a 3D GCM results in which these things are included. But for now, it's just a single column. And when I say something like that, I'm heuristically interpreting what might happen in the real atmosphere. Great. More? Yes. So this is the temperature. We start with 80% humidity or something like that. But in this case, the humidity is very low. I mean, that's a super important question. Thank you for asking that, because I should have said that. Okay. So in this case, we start with 0 temperature and 80 degrees saturation or something like that. So there's not much moisture in the air. In this case, we start with 20 degrees to 80%. So there is lots of moisture in the air. That's why when the warm air moves over North America, condensation can happen and all of these clouds can develop and all of that. Everything depends on this question that you asked, and I forgot to mention that there is lots of moisture in the air to begin with in the warm climate, which isn't the case in the cold climate. That is the reason for these two, the difference between these two scenarios. Yeah, thank you for asking that. What else did I forget? Yes. The single column model is differentiating between liquid clouds and ice clouds, and the green is ice clouds and the blue is liquid. Sorry, the green is liquid clouds and the blue is ice clouds. I mean, yeah. So what happens is you get condensation, and in this case you also get freezing because you started at zero. So whenever there's condensation, it's followed by freezing, and the clouds are ice particle clouds. While in this case, the condensation isn't followed by freezing so quickly, so the clouds are actually liquid clouds. This affects their long wave radiative effects and all of that. Yeah. Although ice clouds would be, of course, very effective in terms of long wave radiation.
Could you explain the time evolution of the vertical?
It propagates up and so on. Yeah, I have some animations showing how this happens. So, you get convection at the surface and the convection propagates up and takes the cloud with it and so on. I'm actually skipping that slide, but yeah, that's what happens here, yeah. So we have another study in which instead of just taking a single column, we take a square domain of, say, 50 by 50 kilometer, three-dimensional, and we see the turbulence and so on, and we see this process happening in more details, and you can see how the convective mixing takes the moisture up and leads to this increase in the height of the clouds and so on. But I guess it's a detail I was about to skip. Yeah. Okay, so we talked about this. Great. Okay. The other thing that's interesting here, we look at the time. Great. Okay, so now you can ask the following question: how long does it take for the temperature at the surface to go below freezing as function of the initial air temperature? So far we've looked at initial temperature of 0 degrees at the surface and 20 degrees, only two cases. Now we can look at the range of initial temperatures. Tim Cronin ran this for a range of this, and now you ask how long does it take the surface to go below freezing, which is the question we're interested in, because there's evidence of frost intolerant species of plants and animals and so on indicate that temperatures did not go below freezing. Okay, so of course, if the initial temperature is 0 or below, then it takes 0 time to get to freezing. But if the initial temperature is 15 degrees, it takes a week for the surface to go below freezing. So again, if the initial temperature of the air is 15 degrees over the ocean, you move it over land, and it takes 15 days to go below freezing. Is that clear what this plot is? Okay. And the different curves are different microphysical packages and all that, but it doesn't matter. They're all basically the same. Okay, so the question is, why is this behavior so nonlinear? There's a very, very small time to get to freezing until about 10 degrees initial conditions. And then when the ocean temperature is 10 degrees or above, this changes dramatically, and now the time to freezing becomes much, much longer. So the question is, what happens? So turns out it's a very simple mechanism. So if you have cold temperatures, this is what the temperature looks like. There's the abrupt cooling initially. That abrupt cooling is stopped when clouds form, because the clouds long radiative effect delay the cooling and stop the long wave radiation. And then once the clouds dissipate, they just fall, they freeze and fall to the ground and so on. Then the cooling continues. So with cold initial conditions, the initial cooling of 10, 15 degrees gets us below freezing. While if the initial temperature is actually relatively warm, then there's the same initial cooling until clouds develop, and the same plateau here, while the clouds are still there before the clouds dissipate, which takes a bit longer because there's more moisture and so on. But this plateau happens above 0. So as long as it's above 0, only after the clouds dissipate do we continue we continue cooling, and that leads to this increase in the time it takes to get to below freezing. This is, few hours to get below freezing, and this could be a week to get below freezing because you have to wait for the clouds to dissipate. Make sense? So that explains this interesting curve here. And the question of time to freezing is, of course, a very important question in the context we're talking about. Okay, so we did this with a three-dimensional model as well, with a summer intern from PKU, was actually now a graduate student in our department who, and we started with pre-industrial configuration, prescribed SST 280 ppm all the way, and then we increased the sea surface temperature all the way to something that doesn't have any SST below 20 degrees Celsius. So a very extreme scenario, and the CO2 is 1960 or something, so corresponds to RCP 8.5 at 22 or 23 century, 2300 century. Okay, so. And then we run the three-dimensional atmospheric model with these prescribed conditions, and we find that in the pre-industrial, the coldest 2-meter temperature is super cold, minus 30 as expected. While if you take this case, the temperatures are not below freezing in this area. So the GCM for this very, very extreme CO2 and SST gives us above freezing cold winter temperatures, cold extreme temperatures. You look at the distribution of temperatures, and this was the original distribution, so probability versus temperature. This is the original one, so it goes from 0 to minus 50 or so. And then in the warm climate, it hardly goes below 0, so most of the temperatures are going to be above freezing. So why does that happen in the GCM now? So you look at this, and this shows you that there's actually a low cloud fraction change in above North America. So just as predicted by the column model, this three-dimensional model produces a very high low cloud fraction, which has a long wave radiative effect, confirming the ideas of the simple column model. Questions?
The parameter governing like cloud dispersion and like the cloud benefits somehow are similar in the GCM to the column model. Is there a sense of, and that's sort of a turbulent structure, is there a sense of how sensitive results are to that?
I mean, in the previous one, we looked at the sensitivity to the microphysics package because microphysics is so important. But I think the question you're asking is not necessarily the microphysics. You're asking about the turbulence and so on.
What causes the cloud to disperse?
Yeah, but that still is microphysics. So they just the ice particles settle down basically, and we've analyzed that. So yeah, the settling speed is about the same in the warm climate and cold climate, but there's more cloud water and more cloud ice in the warm climate because you start with so much more moisture, and that leads to the clouds surviving a bit more. Yeah. You mean here? Yeah, there's plenty of evidence from North America for the Eocene, but I think there is some evidence also in this area, Siberia and so on, that there also the temperatures were above freezing during the Eocene 50 million years ago and so on. And you do see an increase in low cloud fraction as well. So here. Oh, that's right. That's right. It's harder here because if the winds are westerly, basically, they cover a long distance over land getting to this point. So by that time, all the clouds would dissipate, and the mechanism doesn't work as well there. So too bad for these crocodiles over Siberia. I guess we can't explain those. Yeah, that again, there's less evidence in that area, but I think there is evidence that's inconsistent with what this model is showing here. It is what it is. And this is the inversion that was asked about before. So this is the present climate temperatures at 65 north, middle of North America. You have this very strong inversion that leads to very strong cooling during winter time. And in the warm simulations, the inversion is just completely gone. That's super important. I'll talk about the role of this inversion in a second, but the loss of the inversion at the surface is because you're losing the ice at the surface. And the ice is why you have such an inversion, basically, ice, snow, whichever And so losing that means a very significant warming, and you can see that the temperature is 5 degrees at the surface at 65 north, middle of North America. Yeah.
There's a question from online. I'm a bit confused about what you were trying to explain. If you're trying to explain Arctic warmth and you're assuming that the air was already warm enough to have abundant moisture, then in a sense, aren't you assuming what you want to explain?
Great. Yeah. Okay. We're trying to explain the warm temperatures over the continent. It's easy to warm the ocean. That's again something I should have said more explicitly. It's, you can see how the oceans get warmer at the high CO2 and so on, but in the middle of the continent, far away from the moderating effect of the ocean, in the winter, it's going to be very cold. In the summer, it's going to be very hot. We're trying to explain why the winter over the continent did not get very cold. So we allow ourselves to assume that the ocean warmed. Why it warmed is another question. I'll deal with that in the second half of the talk. But the question is, why didn't the continent cool in the middle of the winter? And the reason has to do with these clouds, hopefully, and so on. Yes?
The non-linear response of the temperature.
Yeah.
Time stage.
Yeah.
And do you see some signature of that in the GCX?
We didn't analyze that. You'd have to do Lagrangian analysis of the GCM result, which we haven't done. Okay, so I'm going to skip a bit here. And I'm going to skip this in the interest of time. And so let's jump directly to the conclusions. So conclusions of this part, of the first part. So we said that Arctic air formation today occurs due to the rapid cooling of marine air masses during polar night, due to rapid precipitation of moisture as ice, and long wave radiative cooling. That's the Carey idea. Nice, very nice paper. And we find that if you do the same thing in a warm climate, then you develop these low clouds that have a long wave radiative effect that prevent the cooling and leave the surface above freezing for a long time, a week or two. And the suppression of this Arctic air formation for sea surface temperature that is above 10 degrees Celsius, so that in a warm climate you expect that. This might explain the survival of these frost-resistant species and so on. Frost-intolerant species in Wyoming. And there's also, I skipped that, but there's the lapse rate, for those who know this, there's the lapse rate feedback that is used to explain the Arctic, one of the feedbacks leading to Arctic amplification is the lapse rate, so-called lapse rate feedback in the tropics and in the Arctic, and the inversion is a big part of that. So eliminating the inversion leads to more Arctic amplification. So if you know about that, then you get the idea. If not, it's not important. Great. Any questions, any more questions about this first part before I move to this? Yes. Yeah. Yeah. So, I mean, this assumes that the ocean is warm, including the Arctic Ocean, and only explains what happens over the continent. So I do have to explain what happens over the Arctic. Why would the Arctic be warm enough to allow warm air masses to get, and warm and moist air masses to get into North America? And that would be the second half of the talk. That's right. That's right. That's right. Yeah. So I mean, the idea here was that you have these air masses coming from the ocean, very moist, creating clouds. The air remains above freezing. It moves out of the North American continent, being replaced by new moist air, forms new clouds and so on. So this way, you can sustain the low clouds throughout winter that way. That's the idea. It relies on the westerlies, basically. Okay. So moving to the second half in that case. So this is exactly what we're talking about. So if you look at this paper, 2001, this is one specific air mass starting over Siberia, going over the Arctic Ocean, getting into North America here, the United States during wintertime, February 89, and leading to a very cold event here. So the air mass started in a very cold place, went over the Arctic, which is very cold, and got here. So if we want to explain this warm, moist air coming over North America, not just through westerlies, but also in trajectories like that, we have to clear the Arctic of sea ice during winter. How do we do that is the question. So again, the purpose now is to explain how the Arctic Ocean could have been ice-free during winter. What would be a feedback that can help with that? This is the work of Dorian Abbott and others. Okay, so start with this back of the envelope calculation for the surface temperature of the Arctic. So we have incoming radiation, which is not much during winter. And then we have an atmosphere, you know, the simple atmospheric greenhouse stuff, and surface long wave. And we have heat flux from mid-latitudes. And if you write the energy balance this way, you can now say, okay, what do I need to do to any of these elements in order to increase the temperature of the Arctic surface by 15 degrees Celsius to bring it above freezing? That's the idea, okay? So here's what we do. So to increase the temperature by 15 degrees Celsius, we could increase the heat flux from the mid-latitudes by 1.7 petawatt. Now you expect less heat flux in a warm climate because the equator to pole temperature is lower. So that doesn't work. You can increase the CO2 by 50,000 if you don't take into account water vapor. You have to increase it by 4,000 if you do take this into account. The albedo is not relevant during wintertime anyway, so that doesn't help. This leaves the emissivity of the atmosphere is the solution. So if we can change the emissivity of the atmosphere, then we can explain a large increase in the temperature based on this back of the envelope calculation, and the emissivity is easily changed if you introduce clouds. So that's why clouds over the Arctic can play an important role. Is that clear? Questions? Okay. So just as a reminder, you can think of clouds as being either low or high, just to keep it very, very simple. So high clouds, like cirrus clouds, allow the sunlight to penetrate by trap long wave radiation because of their ice particle composition. And so they have a strong warming effect, strong greenhouse warming effect, while low clouds have a strong reflectivity and are not as effective in trapping long wave because the temperature is close to the temperature of the surface and all that. So low clouds have a cooling effect and high clouds have a warming effect. So we need high clouds over the Arctic. And in wintertime, the whole reflectivity thing doesn't matter. So it really, any clouds would actually help. But if it's a high cloud, that's even better. So we need high clouds over the Arctic. Okay, so we started with this simple toy model that's basically 6 boxes. And it has all of these processes, you know, so advection, convection, clouds, all in 6 boxes representing the equator to the pole. A ridiculously simple model. We got in trouble for that, as you'll see in a second. And then in using this model, we performed the very simple following experiment. We increased the CO2 gradually, and then we decrease. It's kind of an hysteresis experiment with CO2 in the box model, and here's what we get. So what's shown here, this axis is the equator to pole temperature difference. So a high number here means cold climate, because in a cold climate, the equator to pole temperature gradient is high. In a warm climate, the equator to pole temperature is low, okay? So this is cold climate and this is warm climate, right? It's a bit confusing, but you get the idea. Okay, so now when we increase the CO2, you see what happens, the temperature cools, and then there's a jump. And then if you bring down the CO2, there's hysteresis. So at some intermediate value of CO2, the model, this simple box model, has 2 states, one corresponding to a warm climate with a low equator to pole temperature gradient, and another one representing warm climates with a cold climate with a high equator to pole temperature gradient. Questions?
Question from online. How crucial are the clouds in this continental warming mechanism versus just an advection of the warmer marine air?
This has to do with the previous part of the talk. So how crucial are clouds
In the continental warming mechanism
as opposed?
versus just advection of the warmer marine
I see, okay. How crucial are the clouds for the warming in the previous half? Super crucial, because the clouds are what stops the long wave radiative cooling from the surface, and that's why the cooling stops for a while. If it was just dry, warm air, it would radiatively cool immediately, and that wouldn't help. Great. Okay, so continuing with this. So any questions about this part? Great. So what happens? Why is there this jump and why the two equilibria? If you look at the clouds in the polar column, remember, there's a column that represents 60 to 90 north, and that column has clouds in it, even though it's a ridiculously simple model. And it turns out that one of these has the state that is the warm state, this one with the low equator to pole temperature difference, has clouds over the Arctic, and the other one doesn't. And it turns out that what this model does is it develops deep convection and clouds over the Arctic during winter. I mean, it sounds ridiculous if you think about it. I'm talking deep convection of the kind that happens today over the tropics, and it's driven by the sunlight warming the surface and so on. And now I'm telling you that this might happen in wintertime without any sunlight over the Arctic. So you can, hopefully you see that that's a ridiculous claim. Would everyone agree? Okay. But that's the claim. And just for fun, this is an animation of cloud, and you can see convective clouds and so on. So we're claiming that something like that happened over the Arctic in wintertime. Great. Why would that start? So it turns out even if your warming is uniform in height, so this is height in the atmosphere in kilometers, and this is temperature, and this is the temperature before increasing the CO2, and the red line is after. So even if you assume that the warming is uniform in height, which we know it's not, but never mind, then the change to the moisture is, of course, enhanced at the surface because of Clausius-Clapeyron. And the moist static energy at the surface is enhanced at the surface. So this leads to more CAPE and more convection. So that's why warming, even uniform warming in the vertical, is expected to lead to convection. So if in a warm climate you warm the Arctic and you get rid of sea ice, you will get convection. So that leads to a positive feedback. Here's an explanation of the positive feedback. Absolutely.
So this is the delta SC, the changes in your are which the highs. This is the difference between.
No, this is just taking a simple atmospheric model that has a prescribed temperature and calculating and assuming some relative humidity, and then I calculate the moisture in the atmosphere, and then I warm the atmosphere uniformly, and I calculate the change in moisture, and the change is larger at height at the bottom because the temperatures were higher here, if you assume the same relative humidity. So a uniform warming at the same relative humidity leads to an enhancement of the moisture at the lower atmosphere. And that leads to an enhancement of the moist static energy. And if you have more moist static energy at the bottom of the atmosphere, this means more CAPE and therefore more chances for convection. So that's just trying to explain in very simple words why convection is expected with the general warming, even if the warming is uniform in the atmosphere. So that's what happens in this case. Yeah, this very simple calculation assumes fixed relative humidity. It's not that model that I talked about before. So this leads to this positive feedback. You warm the surface, you make the air column more unstable to atmospheric convection because of this moist static energy and CAPE and so on. This leads to deep convection. The deep convection leads to high clouds. The high clouds, we said, have a greenhouse effect, and this warms the surface even more. So it's a positive feedback, and that positive feedback is reinforcing itself and leads to more convection in winter over the Arctic, according to this story. And this leads, and the long wave radiation prevents the Arctic from cooling during the winter, and that therefore, you start the winter with no sea ice at a temperature of, say, 10 degrees Celsius. And because of these clouds, during the winter, the ocean does not cool below freezing and doesn't develop sea ice. So you have an entire winter without sea ice, and that can support the mechanism of the previous talk, where more warm, moist air can come from the Arctic, not just from the Pacific, and create these low clouds over the North American continent and so on. Questions about the positive feedback? Yes.
The vertical profile of the radiative effect of the hypots? Do they have a stronger warming at the surface?
Okay, so in the previous model that I showed, it was a box model. There was only, so there wasn't any profile really. I'll show something else that has a bit more. So let me get to that actually. So yeah, but how do I answer that briefly? The clouds don't have to be super high. The whole high clouds versus low clouds thing that I mentioned before was based on low clouds having strong reflectivity, but in wintertime, that's not an issue. So even if you have low clouds or mid-height clouds at 5 kilometers, say it doesn't have to go to 8 kilometers, that would still lead to a significant greenhouse effect. And we don't need to worry about the cloud albedo. So any clouds would be good, 5 kilometers would be plenty. Okay, we did that analytically too, so you could formulate a two-layer atmospheric model, write the equations for it, find, I'm going to skip that basically. So everything here is done analytically, and you can find analytically an hysteresis of and two equilibria and everything that I talked about. It's kind of fun when you can do things analytically as well, obviously. But I won't get into that because it doesn't add any physics here. Okay, submitted it to review. We got an enthusiastic reception. The first reviewer said this behavior would probably not be of much scientific interest. Second one says this model, we're talking about the simple toy model. I'm a big believer in these toy models. Do you like them yourselves? Great, okay. Second one says this model simulation is incompatible with observations, which I suppose it is, by the way. The third one is the first one review, the third reviewer said that they didn't understand why the model can get equable climate with while realistic models cannot. So why is it that we're getting this convection over the Arctic while realistic models don't get that? That's a fair question, I think, right? And then the editor was super nice to us and decided to send it to yet another reviewer who will probably help us. And that reviewer said that they think that the desired answer is built into the model. Basic data about cloud properties have been ignored. We sent it to a different place. It was published eventually. And we moved on with our life and we moved to, oh, wait. So yeah, I mean, these were all knowledgeable comments. But of course, we were right and they were wrong. I don't need to tell you. I wouldn't be sitting here and telling you about that otherwise, right? So how do we know that we think we're right? Why do we think we're right, right? So for that, we turn to future projections. So you look at two different models. This is CMIP3. No, these are old papers, but I'll show you CMIP 5, 6, whichever soon. This is CMIP 3 looking at the NCAR model and the GFDL model, three-dimensional state-of-the-art at 4 times CO2, and we're showing anomaly from previous climate. So here's what we see. The first line is the NCAR model. The second line is the GFDL model, both at 4 times CO2. So the NCAR model, red means that all of the sea ice is gone from the Arctic, while the GFDL model shows that the sea ice is still here, zero change in sea ice. Okay, so two very different responses of these two models. One shows that sea ice is completely gone in winter, and the other one shows that nothing changes. Next one, the NCAR model shows the warming of 25 to 30 degrees Celsius at the surface, while the GFDL model shows hardly any change. And then you look at this, the cloud radiative forcing here is 20 to 25 watts per meter square. I don't need to tell you how many doublings of CO2 that is. It's huge, right? So this is the epsilon we talked about from the energy balance model. So huge radiative effect due to clouds in this model and nothing in this model. And finally, convective precipitation. So this model shows that there is convection going on at night at high CO2. And this one shows that there isn't. So in a sense, these two models show you the two different steady states that the toy model predicts. So I don't know if the climate system or any of these models actually have two steady states at the same CO2, but it does show you that you can have two steady states, two states in general, perhaps not at the same CO2. One of them has high temperatures, no sea ice, large radiative effect of clouds and convection, and the other one says no convection, no clouds, and cold temperatures. That's exactly what the toy model predicted, which is kind of fun. Right, so we felt vindicated. So completely consistent with the toy model. This is a more recent paper using CMIP 5, and basically what these pictures shows is that 4 out of 5 models show convecting during winter over the Arctic in high CO2 simulations. Never mind the details. So state-of-the-art models, CMIP 5, CMIP 6, whichever, show convecting convection over the Arctic during winter time at high CO2. So the reason people didn't find it, the reason the reviewer asked about that is that no one bothered to look for convection over the Arctic in high CO2 during winter because it didn't make sense. But if you look at it, you do find it in the complicated GCMs as well. Okay, questions? Yes.
Now that I think about it, but if you think about systems like polar lows, these mesoscale systems that they're up there, and they're long-lived and they're small scale, but you think the conditions for the formation of these deep structures has to be, you can assess it. Metrics, and that's built into the parameterization. So
Yeah.
it makes sense now that I think about it.
That you would have that, yeah.
In the current climate, there might be evidence that you have these possibilities of systems there.
Yeah.
Just not necessarily thought about.
Yeah, I guess for polar lows, I guess my colleague Brian Farrell has this theory that it's due to non-normal growth and so on, dry dynamics. So he feels that you don't even need the moisture for that. But I suppose you could have a different mechanism for kind of tropical cyclones in the Arctic that would involve convection. Whether polar lows today involve that or not, I'm
Just broadly, the kind of system.
yeah, that I agree. Yeah.
To what extent are the differences between these like models or the different states are a result of their different like convective and cloud parameterizations versus just existing in two different steady states under the same physics?
Okay, great. I can tell you one more detail about this. I think when NCAR thought about 4 times CO2, they thought about 4 times 300 ppm, which was the sort of the CO2 at the time. Well, this one is 4 times 280. So there's actually a CO2 difference between this. I suspect that if you increase the CO2 here a bit more, it would look like this. So that's the sort of secret behind this.
Other model that actually 1.5, those should have the same.
Right. So yeah. So if you ask what's special about that particular model, this one, why this one doesn't show anything and these do, I mean, it's really difficult to tell. Which one is it? I think this is the French model. Yeah. I didn't say anything, right? I mean, this laughter is not because of something I said. Just to be clear, I have nothing against the French. I had a croissant this morning. Okay. Yeah, I mean, it's difficult to tell in a GCM what is the reason for something happening. Is it the microphysics, the convection parameterization, the cloud parameters? It's just impossible to tell. I think it's called, yes. Okay, great. So I'm safe. I'm safe. I mean, you guys are taking chances. I'm not as brave as you are. Okay, great. Okay, I think we can move to the conclusions of this part. So the challenge in this part was to explain that the CO2 by itself is insufficient to explain how the temperatures would not go below freezing over the continent in warm climates. That is the issue. So it's when we say Eocene warmth, we mean above freezing temperatures in winter over continents. Okay. So we found this simple climate state at house CO2 that is sort of consistent because it involves convection and clouds and long wave radiation and so on, that leads to this positive feedback. As for the future, so if you think about it again, like yesterday, if you have a positive feedback, you could ask, okay, when will this be triggered and might help eliminate winter sea ice? We don't know. That adds to the uncertainty, obviously. So I think it's useful to take a step back and see what other ideas did people suggest for the warmth of the Eocene. So there's this idea about hurricanes, more stronger hurricanes, mixing the ocean, increasing the overturning circulation. This is an idea by Kerry Emanuel. He did further work on that and basically showed it not to be effective using with a student, Corti. And so they showed that that's probably not the case. This is a wonderful idea by Brian Farrell about an equator to pole Hadley cell that might develop in a warm climate. So it's difficult to do that in the GCM. I think this was tried, but it's a nice idea. There's the polar stratospheric clouds idea. So clouds in the stratosphere that would have a strong greenhouse effect, suggested by Sloan et al., and then a dynamical feedback by Kirk Davidoff, Schrag, and Anderson a few years later. And there's the recent paper about breakup of mid-latitude stratocumulus clouds. So the problem with this one is that these are mid-latitude clouds. So how they would affect the continent over, say, the middle of the continent during winter is not obvious, but it's a beautiful mechanism with multiple equilibria and all that stuff that I like. And then the two ones that I talked about today. So this is the big picture. People did come up with many ideas, but 4 of them include clouds. So clouds are probably the place to look, I would guess. Okay, so to conclude, we talked about 2 specific cloud feedbacks that can provide positive feedback and warm the continental interior and are complementing one another. And both mechanisms were confirmed by state-of-the-art climate models. So we start with toy models, but then we try to look at it using more complicated models. And this seems to do the trick. And thank you for listening.